Okay, so now we're going to be talking a little bit about electric dipoles, okay? So what exactly is a dipole? A dipole is when two equal and opposite charges, so in this case, a positive right over here and a negative right over here, they are separated by a certain distance, okay? We're going to go ahead and call that distance, I don't know, L, okay? Or L, whichever way you see it. And this is normally a relatively very close distance, okay? And now we previously talked about electric fields, and well, just like electric fields, I don't know if you remember the electric, the ones that Faraday talked about, where there are these imaginary lines that, you know, go across and like that, okay? And it goes from positive to negative, okay? Well, just like that, there are also dipole fields, okay? And they're very similar. These are the imaginary electric field lines that connect the two charges. And, well, the quantity of the strength of an electric dipole is known as an electric dipole moment, okay? So what this actually means is that the strength, once again, of an electric dipole is the dipole moment, okay? And this is the product, once again. So with product, we know there's a multiplication of the charge, okay? So we're going to go ahead and write that down as Q, okay? And the separation between the charges, so we're going to go ahead and write that down as L, okay? Now, the size of the charge, in this case, Q, it's directly proportional to the electric field, okay? Or in this case, the dipole field. And, well, the amount of dipole field lines double if the size of the charge doubles. So, for example, let's say that we have here a 5... Oh. There we go, my bad. Let's say that here that we have a 5 plus, okay? And here we have a 5 minus, okay? Those are the quantities of the charge, okay? Minus here, and we have a 5, okay? And let's say if we were to double that to, well, 10, okay? So we're here instead of 5, we now have 10. And instead of 5 here, we also have 10. Okay, so if we were able to double the size of the charge, well, that would mean that the amount of electric field lines or dipole lines double as well, okay? So here we would add an extra line. Here as well. Here as well. Here as well. Okay, and that's just an important thing to have in mind, okay? So I'm going to go ahead and write that down, actually. So the size of the charge is proportional to the amount of dipole lines or field lines, okay? Now, that's an interesting fact about the size of the charge. Now, let's talk about the other half of the equation here. What about the length? Okay, so what would happen if the distance between the two charges changes? Okay, if I were to separate the charges, let's say L here, let's say L here is equal to, I don't know, 2 millimeters. Okay, what would happen if I were to change that to 4 millimeters? Also doubling it. Well, what happens in this case is that the dipole field doubles and actually becomes stronger, okay? So these are the connections that these over here are the connections that the charges have within themselves. But just in case you didn't remember, there are also lines going out towards here. Like that, and like that. And, you know, also going forward. I'm just gonna draw the ones for the proton here, okay? And well, obviously they're all going away because very important. The direction always goes from the positive to the negative, okay? And that's why over here they're going towards the negative, right? Okay. So the reason that it becomes stronger is because once it doubles, well, that means that even though they grow farther apart, these lines over here, the ones that I'm currently moving the cursor over, those grow closer together, okay? And that means that the dipole, the electric field, it becomes stronger, okay? Or the dipole field becomes stronger. And well, these are some of the most important aspects, both the length and the size of the charge, okay? And they are the dipole moment once they're combined, which is once again the product of the charge, which is the Q, and the distance, okay, which we can represent as L or D or whatever you prefer, okay? So once again, I'm just gonna write the formula down, okay? So P, which is the product, is equal to the charge, which we're gonna go ahead and write down as Q, times your distance, which you can represent as L or D or whichever you want, okay? Now, just to clarify, orientation does matter, okay? Because negative dipole fields get sucked in and the positive go out, you know, into infinity, or they go out into the electron. But I'm gonna write that down. Excuse me. I'm gonna write that down because it is very, very important, okay? So lines always positive to negative, okay? I'm gonna put that in a big blue square right here. Okay. And let's go ahead and do a little bit of an example, okay? So let me go ahead and make a little bit of space. I'm gonna go ahead and erase these lines just a little bit. We already have an idea of what it looks like, right? And okay. So for example, if we were to have charges Q1 and Q2, I'm gonna go ahead and write them down here, Q1 and Q2, okay? And these were separated by 2 millimeters. I'm gonna go ahead and put each one in. There we go. This is the proton. This is the electron. Okay, so imagine they're separated by 2 millimeters. Okay, and the dipole moment, which is represented by P bar, which is what we have over here, this would basically be Q times 2, okay? Q, which is the charge, times 2, okay? Now, just to clarify, I know I repeat it a lot, but I just want to make it completely clear. The direction of P bar always goes from negative to positive. Okay, so from negative, it would go to positive, okay? Now, the unit of dipole moment is coulomb-meter, okay? The coulomb being the charge, which is right here, and meter, you know, that's the SI unit. In this case, I chose millimeters, but the standard international unit would be meters and coulombs, okay? Coulombs and meters.